This is a high-level, top-down based approach to applications of sensor networks. A little bit of stochastics with my research field of lighting and lighting control. This work is done at the MIT Media Lab in Cambridge with the principal investigator, Zhao Paradiso. So we'll just jump right into it. To give you guys a background, we have a corollary to Moore's law, and this is Haitz's law, that more or less talks about the growth of LEDs as well as the cost per lumen of these LEDs over time. And so this is basically saying that as similar to the fact that transistors double every 2 years, we have the similar effects with lighting and lighting technology. Now, to give some background of sort of why we think of lighting and lighting control in this group, a result that people may not be so familiar with is this work that came from Jeff Zhao from Sandia National Laboratories. And what these graphs are really saying is it's saying that as the energy efficiency or the efficacy of lighting technology has increased over time, instead of saving energy, what we found is that we found more ways of consuming lighting. So we've actually increased our consumption and found new applications and ways of using lighting. Sort of the opposite of what you'd expect. This is similar to trying to remove congestion in a highway by adding lanes, only to find a month later the congestion's back. So to move into some of the applications and things we've done, other related work from other groups is in the paper. But one of the first things we took a look at was a sensor-based approach to measure intensity of modulated light sources, as well as estimate the background illuminance in order to basically infer the contributions of light using the inverse square law and use that to optimize the overhead lighting. So here is like a typical test setup, and we looked at time-based schemes as well as frequency-based schemes, and then those are given in the references below. We've moved from sort of that sensor-based approach to a more wearable type of infrastructure in some of our later work. So here is a project where we took the same sensors and added the IMU-based measurements to sort of look at a control interface for not only lighting but also HVAC. This was called the RISC-K, and in here we added the IMU, so you can now point and gesture as another way of interacting with the space. So just before we jump into the work, just to tie things back together, my work tends to be mostly in the areas of human-computer interaction. To that end, we do use sensors, but we're not necessarily conducting the basic research. And to give you guys a flavor of sort of HCI, 20 years ago, Mark Weiser put forth this notion that eventually the electronics and the sensors and our computing platforms will tend to fade into the background. And so to that end, one of the things that we did was a couple years ago, we presented a paper here at IEEE Sensors that was a large-scale visualization of real-time sensor data that allowed you to sort of participate and fly around and move around in this space. And so the idea was to focus on, say, presence and sort of interaction with these environments. So the work today is really going to focus on measuring humans and how humans move and how those movements and recording of those movements can be used to sort of manage building utilities, in this case lighting. So in this experiment, we have a pretty vanilla board here, just a low power radio, an MCU, the photodiode, the PIR, and the base station. And so this was replicated 34 times across the lab. Or across our space. We had a lifetime of 8 to 12 months, which was fine for running the experiment. And so here's just a visualization of the actual experiment. So those green dots are the sensor nodes in the space. We tried to make it as close as we could to a regular lattice. The sensors were magnetically coupled onto the overhead light fixtures. Like I said, 34 nodes, and 3 research groups actually occupied this space. And so we sort of observed occupancy as well as light data over a range of 8 months. So the first part of this paper, this notion of random walk, arises when you want to deal or sort of allow the system to learn basically patterns of occupancy over time. A Markov process tends to be a great way to do this because there's a dependence in a prior state. So what we did here is that there's two basic things that you're interested in looking at when you try and model occupancy. And in this case, we wanted to figure out the percentage of time that nodes were either occupied or unoccupied, and as well as sort of calculate the number of transitions in this sort of random matrix that could allow us to infer the actual optimal time to turn the lights off. So what's interesting for the use of PIRs is not necessarily predicting when people will be there. That's important for HVAC. But for us, it's minimizing type 2 errors, with the fact that these sensors could be turned on or off. So there's more details in the paper, but then just to keep it general, we don't get too deep into the weeds here. So there's a couple other things that we did in this paper. The other thing is looking at presence and flow, and we know that movement in the network isn't entirely random. You can see that there's a time dependence between 2 in the morning and 2 in the afternoon, but it's a lab, so maybe it could be busier in the morning. But movement tends to be correlated, and you end up getting these local loops in this visualization here. So one of the things that you can actually do is you can take a look at the data that you measured, and you can consider these techniques where you may want to apply some type of spectral decomposition. And so what this graph is really showing you is it's showing you that within the data that we measured, you are able to find sort of clustering and local flights within this network. And so these four peripheral areas actually refer to the boundaries, the naturally inferred boundaries of the 3 research groups that we have in the space, where that fourth part in the middle, the green, corresponds to a soldering area. So as you might expect, we tend to be territorial, and you might infer that. But the other thing is that from a building design perspective, one of the interesting applications is that this means that you could possibly allow the system to automatically zone areas of lighting, automatically zone for HVAC. So the applications for something like this, especially in the use of like cyberphysical systems, is important. So just to conclude this presentation, what we've done is we've sort of taken an agent-based approach to the modeling of occupancy in the sensor nodes. These algorithms, they can run at the per node scale. So it's possible that the system could learn over time. It could be local. And then we've sort of learned we've shown how you can infer sort of, social context and the actual boundaries of where people tend to walk and move in the network. And of course, in these types of applications, privacy tends to be a big concern. And so this was all accomplished with off-the-shelf PIR sensors. So again, I thank you guys for your time and for your patience. This is a picture of the group. The PI is actually on my left in the corner. For any of you guys who happen to care or are interested in our lighting-related work, here's the link. Thank you.